Last time we already started the topics of the quantization of SHO. So what did we learn? The first thing we emphasized that position operator and momentum operator are just an operator. Now, if it's difficult to understand, think of it as a matrix. And it's so special because if you apply position operator to any position state, you get a number times that position state. So that means the position state, whether your particle is at certain position, is the eigenvector of this operator. And its eigenvalue is exactly just the position that you have. Similarly, for the momentum operator, if your particle is at a certain momentum, you apply the momentum operator to the momentum state, you will get the momentum. So the momentum is the eigenvalue of the momentum operator, and the momentum state is the eigenvector of the operator. There are lots of things you can think about, right? But because of time, we will just stop here. But I would like you to appreciate that you can have something called position operator and something called momentum operator. With that, then we say that in the last two lectures, we talked about the Lagrangian mechanics and the Hamiltonian mechanics. And what's so special is that once you wrote down the Hamiltonian mechanics, and you write them in terms of in this case, the position the position as a function of position and momentum, you can go to the quantum regime or a quantum framework right away by promoting the position to the position operator and the momentum to the momentum operator, right? For example, a simple harmonic oscillator has this Hamiltonian as p squared divided by 2m plus kx squared divided by 2. P and x are the two variables. And we just promote them to the operator, then we get the quantum version of the simple harmonic oscillator. Again, we did not discuss too much why this is the case, but we will just accept it for this class, right? But I hope that you can see the linkage. We have the Hamiltonian, and then we promote the position and momentum to operator. And with that, then we will see the effect of quantum mechanics. So how? First of all, I also forgot to mention again, the position operator and the momentum operator. Remember, now they are operators, so they are matrix. So matrix do not necessarily commute with each other, right? A times B is not necessarily equal to B times A. So we have this commutator x and p, which means it's xp minus px. If xp equal to px, of course this is 0, but indeed it is not. It is IH bar. Although IH bar or H bar, the reduced Planck constant, is very small, but it is still not 0, right? So with this, then we define something called annihilation operator and creation operator. This is sometimes called destroy operator. Based on this name, you probably will guess, yeah, this is the A dagger, A head is going to destroy something, and the A dagger head is going to create something. But we have not proved it yet, right? So, but we take it for granted for now. And it is just a function of the position operator and momentum operator. And they are the complex, they are the adjoint matrix of each other, right? Because A dagger equal to A dagger equal to A, right? And these are just definition. We went through this complicated math, but should not be complicated. You should be able to do it just to appreciate again why you should keep track of the position of each variable when you do multiplication. xp is not equal to px. That's why you cannot cancel that. And go through all the math by using the fact that xp, right, equals to IH bar, xp commutator equal to IH bar. We find that A dagger also do not commute with each other, and the value is 1. Is that okay? right? So we don't go through the math again, but here we learn another thing. A dagger equal to 1, right? Just put in your cheat sheet, or you know what to look for when you need to derive any equations. With that, we further introduce another operator. We call it number operator, right? The name is very appropriate. You probably already guessed. Maybe this number operator is related to counting the number of particles in a system. And combined with this creation and annihilation operator, you probably can guess that, oh, it must be an operator. You can increase the number and reduce the number. Again, we have not proved it yet. Right? But the point is, we define number operator as A dagger A. And we already know what is A dagger and A. Just plug in, do the math very carefully. Always remember X and P do not commute. They equal to IH bar. You go through this math, eventually you find that this N is related to the Hamiltonian, which is the total energy of the system. You rearrange it, you find that the total energy of the system equal to h bar omega naught. And you know that this is just the energy of one photon, right? Any photon, right, has a frequency of f, its energy is h times f. If you forgot from your basic physics or you did not learn that before, then you just take this for granted, okay? So if you have long wavelength photon, its energy is smaller than the short wavelength, right? And that's why X-ray can cause body damage, but infrared will not, because X-ray has a higher energy for each photon, right? So, but this equation tells us something. The total energy of this system is equal to a number operator times the energy of one unit of photon, for example, right? Although it has an offset, but this kind of explains why N is called a number operator. Again, we have not really looked from every aspect so far, right? We only show that, okay, A dagger equal to 1. The number operator has a relationship to the total energy through this h bar omega N with this 1/2 offset. Then we continue to explore the meaning of N. So what we did last time is we apply N to its eigenvector. We assume it has an eigenvector called capital N. And then, of course, it will have an eigenvalue. We call it capital N also. Then we apply the Hamiltonian to it. Hamiltonian is h omega N dagger, right? We go through the math, and eventually we show that if capital N is the eigenvector of this operator, it turns out it's also the eigenvector of the Hamiltonian. So basically, say that in your simple harmonic system, you have a state called N. And this N is the eigenvector of capital N, which counts the number of photons. We assume that. And it is also the eigenvector of the total energy. It means that if you know the number of photons in this single harmonic oscillator, you know its total energy also, right? So with this, then we say, we just set En equal to h bar omega N. This is not operator. Again, this is the eigenvalue of the capital N, right? So based on this, we can interpret the result as this is the energy when you have capital N number of photons. Now, maybe still confusing, but now let's just take it for granted. We say, okay, the amount of energy for a simple harmonic oscillator is just h bar omega capital N plus half. We prove it, and we show that it is consistent from every aspect, because if I apply the Hamiltonian, I do get this as the energy. And then I also convince myself capital N is the number of photons inside the system. However, we still have not determined what is the value of An. Can it be negative? Can it be fractional or even irrational? Right? But if we accept N, now we just the number, half or half photon, whatever, let's assume it is okay, then everything works well. But next then, what we need to do is to prove that this capital N has to be positive or integer, including 0. Is this okay so far? Okay, so everything is just the math, right? So, but we need to go through this. Okay, so this is what we need to do. First, we want to check, actually we need to prove. Don't know why I say identity. Okay, since N, A hat, what is this by definition? N, thank you. N A hat minus, N hat A hat minus A hat N hat. Okay, so I'm going to plug in N. Do you remember what is N in terms of A and A dagger? Probably forgot. It's A dagger A. Okay, A dagger A by definition. So I'm going to put this as A dagger A, right? A dagger, A hat, A dagger A. Is this okay? I just substitute N by A hat A, and then N by A hat A, and I write this as this. Okay? And so I can factorize this out as, I just factorize the A from the left. Okay, I pull out this A from the right. I pull out this A from the right. So I have A dagger A minus A dagger. Okay? Just a trick, right? But if you remember, A dagger, they don't commute. But what is the value? Do you remember? 1, thank you. So, let me write this down first. This by definition is A dagger minus A dagger A. This equals to 1, right? So this can help me find out the value of this guy. So what is the value of this guy? -1, very good. Right, so this one, it means that A dagger A dagger A minus A dagger equals -1, right? So basically we're saying this one equal to -1, right? So we can have the conclusion say A, therefore A hat A, N, I keep saying the wrong thing, N A commutator equals to -A hat. Okay, so similarly, I would like you to prove this in your homework. If you ask about N hat A dagger, it is equal to A dagger. Okay, so here, nothing special, right? We just go through the equations. But I hope that you are very familiar with this math operation. Okay, so we get 2 equations from here. Right, again, it's the commutation relationship between 2 operators. NA equal to -A, and then NA dagger equal to A dagger. Okay, any questions? Yeah, so let's keep this equation, keep this in mind. Then now let's try to understand the meaning of creation and annihilation operator. So again, people already found out how, right? But we just show it. If I apply N to this state, now this is very important. This is something that's some skill we always use. What is the meaning of this? Let's just explain it in English. You mean apply N operator to this. But this as a whole, what is this as a whole? Is this a matrix or a vector? vector, right? It is not an operator, it's a vector, right? It's just that I apply an operator to a vector. It's a state. I apply A to N, and of course I get a state. So basically it's saying that what happens if I apply the lumber operator to this state? Right? So this is a state. Right? This is a state. So what happens when I apply to it? That's the question. So I'm going to just naturally I can do the associative rule. I break this. I break it, right? And now, but however, from the previous line, we say that NA equal to negative A. Right? Previous slide, we say NA equals to negative A, and NA of course equal to NA minus AN, right? So which means NA equals to AN minus A, right? So what I'm trying to do is that I know there's a trick, so I want to use this commutator relationship, want to substitute that relationship to NA. So this one is NA minus AN for this commutator. So NA of course equal to AN minus A. Okay. So with this, then I know that this is equal to AN minus A applied to N. Right, for this one, I plug in NA equal to AN minus A. So with this, let's take a look. What is N applied to N? And what is A applied to N? What is N applied to N? N hat applied to N. Do you still remember their relationship? So can I say again? N. Because we say that, we assume that capital N is the eigenvector of this N operator, right? So it's equal to NN. So this one basically say that this equals to A hat N N, right? The only difference is that this was an operator, now becomes a number. Right? And the second term, I don't change it. Now, because capital N is a number, I can put into the front. I can do whatever I want, right? So this, I can factorize it as N minus 1 A hat N. Right, do you see that? Because this is a number, I move it to the front. So sometimes you get confused, then think of it from matrix point of view. A hat is a matrix, and this is a pure number. Number can go in front of the matrix, no problem, right? And this is a vector. So I have N times AN minus AN. Then of course it's equal to N minus 1 times AN. A hat N. Make sense? But now if you look at this again, at the beginning we have N applied to this state. This is a state. And at the end, I get N minus 1 applied to the same state. Right? Basically, we have proved that I apply the number operator to this state, I will get N minus 1 times that state. Then what does it mean? It means A hat N is an eigenvector of N hat. Correct? Because I apply N to this state. equal to a number times this state. Then, of course, this is the eigenvector of n hat, right? But more importantly, it says that with an eigenvalue, what is the eigenvalue of this state? Correspond to this state based on this equation, huh? N minus 1. Right? Because you say you apply the number operator to this state, we don't know what this state is. It gives me eigenvalue of n minus 1. Then it means what? Then it means A hat applied to n must be equals to something, a number times n minus 1. Right? Yes, this number we need to determine this is just a real number or a complex number. We can make it real. But basically say that this state A hat n equals to n minus 1 state. And earlier we claimed that this n corresponds to the number of photons in this simple harmonic oscillator. So we say that you apply A to this state, you become another state which has n minus 1 number of photons. And now it makes sense. I apply this annihilation operator to the n, I get n minus 1. And that proves the naming, why we call it annihilation operator, because it destroys 1 photon. The system used to have n state, now becomes n minus 1. So I keep saying photon, but I mean quanta of energy. Okay, not necessarily photon. Any questions? We can pause a little bit, make sure that you understand. Any questions? So again, this is just proof. I really hope that you can go home and try to prove it. We have the similar thing in the assignment. But the most important thing here is that you realize that A applied to n equals to n minus 1. Now, but however, I cannot say equal to n minus 1 because this might not be normalized. Yeah. A hat dagger matrix, right? Yeah, we are going to look at it later. Yeah, I will show you the form. Yeah, good point. Let's look at it later. Okay, so now I need to determine the D minus, right? Because from the previous slide, we claimed that, we showed that, we proved that A applied to n equals to D minus just a number n minus 1. So what is D? Okay, so let's consider the inner product. Or, consider the inner product. Right, just because people already see that how to prove it. So we consider the inner product, which is of itself. Which means try to get the square, right? By the way, maybe you can tell me, right? How do I find the inner product of, the length of A hat n? How do you find it? How do you find the length or the length square of this state A hat n? Or how do you find the length of a vector? Inner product, yeah. So how do you write it? What I mean is just what is bra version times this, that's what I try to fish for. But what is the bra version of this guy? Can you? Very good. Bra and A dagger, right? And then the other side is AN. Because the matrix need to get the adjoint matrix, right? So it's A dagger. Okay, good. Now with this, then I substitute what I found earlier. This is equals to maybe I start with the cats, then it will be easier. A dagger A n equals to D minus n minus 1, right? A dagger A, the cat. Sorry, I keep saying the wrong thing. A dagger n equals to D minus n minus 1. So A dagger n equals to D minus n minus 1. Is this okay? How about for the bra version? If I want to use this equation. Also n minus 1. D minus star. Right? So here we get some confusion, because if you try to do the bra version, on the left it is n A hat dagger. On the right is what? N minus 1 D minus star, because D is just a scalar, complex number. Now, does it make sense to you? A dagger is this one. The bra version is n A dagger, right? Make sense? Because for bra, you need to take the adjoint matrix. So dagger, right? And this one is just a pure number times n minus 1, so it becomes the bra version times the complex conjugate of the pure number. So that's why I get this one. Right, so this can be confusing. That's why you need to be careful. Now, of course, this is equal to what? What is when you have a number times its complex conjugate? It's just equal to its magnitude square. Right? Because this is, let's say, I star times I. That is just equal to I magnitude square. And then this is n minus 1, n minus 1. Is that okay? Now, of course, we already know this n must be normalized, right? N use all the numbers, right? So this is just equal to D minus square. That's the first thing, right? So this is 1. Now, second, let me change another color. This guy is just equal to n hat n. Why? Why this is equal to this one? Yeah, because A dagger A is n, as we defined earlier. A dagger A equals to n, right? So I continue. Now, can you simplify it? What is this? Just n, because this is n, but this is also n now, because n dagger apply to n. The matrix apply to the vector, because it's eigenvector. So I get the eigenvalue, becomes a number times that vector. I think in that way. And if n is a number, then of course this is just equals to, I can take the number out. This is confusing, but it's simple. And then it should be normalized. So this is just equal to n. Right? So basically 1 and 2 give us n equals to D minus square. Right? Because this guy equal to D minus square. This guy equal to n. Yeah, so I have many choice, but I can just choose D minus equals to square root n. Okay? And what does it mean eventually? It means, this is the equation, A applied to n equals to square root n, n. It means that you apply the annihilation operator to the state capital N, you get, you find my mistake, right? Should be n minus 1. Very good. You apply this annihilation operator to capital N, you get another state with one less quantum of energy, but scaled by square root n. This one is normalized. No, not normalized. Scaled by square root n minus 1 is normalized. The whole thing is not normalized, right? But the point is just you have this relationship. So in your assignment, I would like you to go through the same process, right? And show also, you can go through the similar process, find the similar equation. You get A dagger n equals to square root n plus 1 n. This is another equation. Now, how do I memorize it? Definitely, you know, if you apply A, you reduce the number, right? Because annihilation operators begin n minus 1. You apply A dagger, you increase it because it's a creation operator. So I make a mistake again, right? No, okay, should be plus 1, right? You create one more quantum of energy, right? Then what should be the prefactor? It's easy to memorize square root and then always memorize the largest number in this equation. So this is capital N larger than n minus 1, I put n, right? So this is n and n plus 1, I put n plus 1. That's how I memorize the equation. Then you won't get wrong, okay? But definitely you should know how it changes the state. Any questions? Yeah. Positives. So yeah, then you will add a phase, right? You will choose negative. Then I think it will still work, but I never try. I believe it still work, but just will it still work? I don't know actually. Maybe if you go deeper, this is more reasonable. But yeah, because the phase is not important, right? From observable point of view. So I believe you can choose other way, even imaginary. So instead of you asking why positive and negative, is that we can choose I or negative I, right? I think you can. Probably you can. Maybe I can be wrong. I never thought about this. Yeah. This n, right? Capital N. This is the eigenvector, yes, of n hat, yes. But he's asking why this need to be definitely square root n, but can we have prefactor like I times square root n, just e to the power I phi, right? In general. Yeah. Correct. So when you are trying to really look at the physical phenomena, this e to the power I phi is not important, right? So first, of course, it is not important, right? But I just don't know if in deeper physics actually they have some implication, right? They may say, oh, this does not align with fundamental physics or something. Like they keep deriving. So I don't know actually. I just choose positive. So that's a good question. Maybe you can ask those experts in your physics class. Okay, but anyway, the point is this is what people have been using, square root, yeah, positive, yeah. Okay, so we agree that n counts the number of quantum or quanta of energy. We agree that the creation operator create one quantum of energy. The annihilation operator destroy one quantum of energy. But we still don't know what are the value of capital N. Is it just 1, 2, 3, 4, 5, 6, or it can be 1.1, 1.2, right? So this slide is to study this problem. Again, looks like not directly related to our class, even you don't know this, but it's just a good way to practice, right? So that in the future, study some more difficult problem, you have some foundation of that. Okay, so now let's again look at the inner product or the norm. Let me just call it the norm, right? The norm, which is the inner product square root, right? But it is the norm of a, actually norm square of a n. And of course, it is the inner product which we just studied, which is n, a, dagger, a, n. Is this okay? We just studied, right? So I'm just repeating what we say, and this equal to n hat, n, which is equal to n, right? Because a, dagger a equal to a hat, and a hat, again, this is the eigenvector, I get n, and then n dot n is n, so this is just n. We know that already, right? This is the norm, but we know that. But norm or the inner product of itself must be positive or larger than 0. I mean, equal or larger than 0. Right? This one we actually, why we have this definition, and even remember? Why I say that? Because this was the definition of inner product. Remember, at the very beginning of the class, the definition of inner product is that it satisfies a few criteria. One is the norm need to be larger or equal to 0. Right? This is like see the definition of inner product. I think maybe in chapter 2, right? In chapter 2. So it need to be like this. Now, but norm is equal to n, right? Then what it means? So it means n must be larger or equal to 0. So that, right? You cannot have negative. You cannot have negative n, which is good. That is aligned with our expectation. However, can it be long integer? So we prove by contradiction, for example, right? So assume n can be long integer. If it can be long integer, right? For example, so it's not really a proof, but just an example. Then a dagger 0.5, let me write it clearly, with n equal to 0.5. What will you get based on everything we have learned so far? When you apply a to n equal to 0.5, what will you get? Thank you. Equal to n square root times minus 0.5, right? Because this is n minus 1. Correct? But this contradicts what we say. The fact that n need to be larger or equal to 0. Right? So if I allow long integer n, let's say 0.5, 1.7, I apply the annihilation operator, I will keep reducing it, right? Keep reducing 1, 1, 1. Eventually, it will become negative 0 point something. And then this is valid. I do nothing wrong in the math. Then it means I can get a state that is negative with negative n. But I already proved that n need to be larger or equal to 0. Right? So that's why this is not proof by contradictions. So that's why n must be an integer. And why? You may say, okay, if it's integer, I keep reducing it, eventually it becomes 0 state. So what happens if it is at 0 state? Right? So applying A dagger will reduce N to 0, right? Eventually it becomes 0. I keep applying A dagger. I mean, keep applying A. Then what? I still can apply one more time, right? A apply to 0. This is allowed, right? No quanta of energy. But based on the equation, what do I get? I will get N times 0 minus 1. Then you may say, hey, then you have 0. But unfortunately, the coefficient is also 0. So this one will give us 0, not 0 state. Just don't have the state, right? And everything stopped there. Now you apply another A to it, it is still 0. Then the whole system becomes consistent, right? So these are the trick. So based on this, now we are very confident. So I will say N hat is a number operator with and maybe I say, and then N hat means I have N number of quanta of energy in this system. Right? Because now everything makes sense. It has need to be either 0, 1, 2, 3 natural number. So yeah, so now if I say this way, you see that capital N is the number of quanta of energy in SHO. I apply annihilation operator, it reduces it by 1. I apply creation operator, it increases it by 1. I apply the number operator, it will tell me how many quanta it has, the capital N. I apply the Hamiltonian, it tells me the total energy, which is h bar omega n plus half. So everything makes sense, right? Although the proof are pretty, a little bit looks cyclic, but that's okay. Yeah. Any questions? Okay. Let's learn a little bit more about this energy eigenstate. But let me remind you, this energy eigenstate is also just the number eigenstate. Okay, capital N. So let's, these are just for some equation, right? So let's do this. What happens if I apply this? We did not prove it, but I show you the equation. See if you remember. Apply. So I start with a state that has 0 quanta of energy. Apply the creation operator, even without the math, just based on English. Apply a creation operator to 0 quanta of energy. What will you get? 1, because I create 1, right? So very good. So then this must be 1. Of course, I also need to make this as a square root 1. Yeah, because of the equation. So based on this, I can say state 1 is equal to A dagger hat applied to 0 divided by square root 1. All I'm doing is just reshuffle the equation, right? State 1 equal to A dagger 0 divided by square root 1. Then let me continue. How about A dagger 1? What is this? Creation operator applied to a system with 1 quantum of energy. I create 1 more, becomes 2, right? And then the prefactor is square root 2. So then it means what? 2 equals to A dagger hat applied to 1 divided by square root 2. But I already know what is 1, right? I continue to substitute. This becomes A dagger hat, A dagger 0 divided by square root 2, square root 1. Right? So what I'm doing is just substitute 1 to here. I have A dagger divided by square root 2, and then 1. 1 is A dagger 0 divided by square root 1. Is that okay? So let me do one more time. How about A dagger hat applied to 2? What is this? Square root 3, right? Which is equals to 3. Implies that 3 equals to A dagger applied to state 2 divided by square root 3, right? Then I substitute the one from above for state 2. This is A dagger hat, A dagger hat, A dagger hat, 0 divided by square root 3, square root 2, square root 1. I did not prove anything. You can do this by induction or whatever you want, but you already see the pattern, right? So it means, what is n? N can be written as A dagger, apply it n time to 0 state, which makes a lot of sense. If you have a system with 0 quanta of energy, you create n of them. Means you create 1 for n time. Of course, you get A dagger capital N, right? And then, of course, you need to normalize it by square root n factorial. Make sense? So that's just an exercise. Any questions? Okay, these are just math. Now, then go back to our question about the matrix of the creation and annihilation operator. If you want to write the matrix, the first thing you need to do is determine what is the computational basis. Okay? So, in the basis of n, right? You can have many different bases, but I decided to use n, the number of quanta, as the basis. What is the dimension of this basis? Or ask yourself, what is the possible value of n for a simple infinite? So you go from 0 all the way to infinity, right? Which is 0, 1, 2, all the way to infinity, right? So first of all, this is the first thing. Then what is the size of the matrix? It has to be infinity. Okay? Now, then I will just give you the answer. And then we look at a simple case. It turned out that this A hat, if I wrote it in this basis, it will be, first, it's infinite, so it's difficult for me to write. But I will write down the diagonal one. The diagonal is 0. Okay, the diagonal is 0. And then everything else also 0. Okay, but the one next to the diagonal on the right is square root 1, square root 2, square root 3, and then you just keep going. So one diagonal, I don't know how to say this, one diagonal above the diagonal, right, is square root 1, square root 2, square root. So I say something wrong. This one should start from 0, so this is not. Let me redo it. I say something wrong. Let me redo it, right? Because we start from 0, it's infinite in one direction, but not the other direction. So I have 0, 0, 0, 0, and then just keep going. Then the element here, square root 1, square root 2, square root 3, right? Square root 4, and you just keep going. And then the rest is 0. Now, again, why this is the case, you can think of it, the first line refer to 0 state, second line refer to 1 state, third line referring to 2 state, right? So for example, in the 2-level system, we will study soon, right, for simple harmonic oscillator. What is A? In the diagonal direction is 0, 0. I just said it, right? But then the one higher to it is you start with square root 1. And then the rest are 0. So this is the annihilation operator for a two-state system. Let's check. For example, if I apply A to state 1, I need to destroy 1, right? But what is state 1 in this notation, in this spaces? It is 0, 1, right? Because the top is 0. So let me just emphasize again. This row represents 0, this row represents 1. You apply this to it, what do you get? You get 1, 0, which is equals to 0. Right? So you do get A applied to 1 equals to 0. And regarding the prefactor is square root 1, so no problem. Right? And indeed, this 1 is from here, square root 1. Now, what if you continue to apply another one? Because this is a two-level system. If you try to apply again, in this direction, you will go to 0. But not just two level, any level, this will just bring you to 0, right? The number 0. Let's look at the raising operator. That would be... So you probably can guess it is the same. Except that now you put it here. The non-zero term is the diagonal at the, lower than it. So square root 1, square root 2, square root 3. And then the rest is 0. And again, the easiest way to look at it is, you can try 3 level, right? But here I try 2 level. 2 level means that you only have 0 or 1. And what do I get? A dagger. Again, by definition, diagonal are all 0. And the rest are 0. The one lower than it, the lower triangular place, is start with square root 1. Right? Which is equal to 0, 0, 1, 0. So let me check. Apply this to 0. I would expect to get 1. So let me put that 0, 0, 1, 0 applied to 0, 1, 0. This is equal to 0, 1. Indeed, this is equal to 1, which is equal to square root 1 times 1 state, right? Now, what if I do one more time? A dagger A. Now, if this is an infinite system, you know this will bring me to 2. But however, I limit it to the 2 dimensions. So if I bring it to 2, it's meaningless to me because it exceeds my Hilbert space. And indeed, you see that this will also capture it because now I apply to 0, 1, right? This is equal to 0, 0, which is 0, right? So yeah. It failed, it just become something meaningless. It's not because the physics failed, but if your physics, in your physical system, you really only have 2 level state, and indeed it's meaningless to say I add one more quanta to it. Okay, so that is the matrix form. So the most important thing is remember how to write the determine the basis that you want to write the matrix for. And with that, then you will be okay. Okay? Good. Any questions? If no, I want to do something just for your knowledge. It's not very important for this class. We have been talking about bracket, and some of you already learned about simple harmonics oscillator in the real space, and usually quantum mechanics start with that class. Right? How to talk about the wave function. But before that, let's look at this energy diagram. We have a classical potential energy, which refer to half kx squared. That's about the spring, right? And of course, we also have kinetic energy, which you cannot see. But here we already quantized it based on our quantization. We say the energy En equals to h bar omega naught capital N plus half. So basically it say that you only can have this discrete energy level, and their spacing are the same. This is very important. You need to realize that they have the same spacing, so they are not good qubit, because you have state 0 and state 1, you can go to state 2 easily. Right? We will discuss the anharmonicity in the future. But basically this is not a good qubit. But I quantize it. I do get 2 levels, actually more than 2 levels. So this is the picture. Right? But how is this related to our wave function? Remember, here we only talk about the states. Here is talking about this corresponds to state 0. This corresponds to state 1. This corresponds to state 2. So this is the state. But we did not have any information about how they distribute in the real space. Right? The probability of finding them in a real space, or the probability of detecting is momentum. We just say state, because this is another basic. We say, okay, this is how many quanta of energy. Okay, just another. So how is it related to that? So in order to find psi x, we basically need to project the state, for example, 0 to x. Remember, x is an eigenvector of the space we talked about earlier. You have the x hat applied to x, you get x times x, right? So these are 2 different descriptions, right? They are not the same state, but they're 2 different bases. Now you're projecting from z basis to x basis, like what we did earlier. So if I want to know what they are, I will do projection. So basically, it's like this. I project this 0 state to x. Then, of course, this is the so-called wave function in the real space of this state. Okay, and this is the solution you got if you try to solve the Schrödinger equation in the wave form. Okay, so let's go through the math a little bit. But since a dagger applied to 0 give you 0, right? Because you lower the operator, then it means x a dagger 0 equals to 0, right? Because then it means a applied to 0 give me just 0, then times this one, of course, it is 0, right? But what is a dagger? We know that. We learned that earlier. I'm not a dagger, sorry, a hat. I keep saying the wrong thing, a hat. This one equal to square root m omega 0 divided by 2h bar x hat plus I p hat divided by m omega 0. Right, so what I'm doing is very simple. I just say that I try to find the inner product of x of a 0, right? A applied to 0 is just purely a number 0. So this is equal to 0. Then I substitute a with this definition of annihilation operator. And then I can do distribution rule, right? This one, the first term give me x hat 0, right? The second term will give me I over m omega naught x p hat 0. I have a question for you. Where is this square root term? Thank you. because this is positive, right? I just remove it. This is 0 here, right? So this term is gone. So I have x hat 0, the first term. X I over m omega naught, I take it out. X p hat 0. Okay. Now here we did not really prove it, but let's do it step by step. What is the meaning of this one? I can apply x hat to 0, but this is 0 state. So okay, so now it becomes a little bit confusing, right? Some of you should remember this 0 means n equal to 0, not x equal to 0. Okay, this is the lumbar eigenstate 0, because I want to project n equal to 0 to x, right? So I cannot apply this to here easily, because this is not x equal to this n equal to, but I can apply it to the left, right? When I pass x hat to x, what will happen? Just x, because it's the eigenvector, right? So I can take this out, this become x times x 0. Right? I apply this to here, becomes x, right? Apply this one, because this is the eigenvector of x hat. So I get hat x, right? Now this part, you just take it for granted. It turned out that you apply the p to x, you actually is getting a differential term. You learned this in your quantum mechanics, so if you don't know this, just ignore it, just take it for granted. Because this is related to the, if you do the translation, right, the momentum is the generator of translation. You go through this, you will see this term over there. So basically, what I try to say is that you go through this, and then this one is just equal to psi 0x. This one is also psi 0x. So we have convert this bracket notation or this term to an equation. And now if you solve it, solve this differential equation, you will get psi 0x equal to 1 over pi to the power 1 over 4 square root x naught exponential minus 1 over 2x divided by x naught squared, which is this wave function. So this will not test in the exam, but I just want to help some of you who want to pursue further in the future to understand the relationship between this lumbar eigenstates, how many quanta you have, to the wave function in the real space. And the main message is that to find that, project your states into the eigenstate of the x. If you want to find the momentum distribution, want to represent this state in the momentum eigenstate, you project this to the momentum eigenstate. And this is what we are doing. We project it. But of course, it's not straightforward. We have some trick to come up with the equation. And eventually, the equation has the projection that we want. So this is psi of x. And it's a differential equation. And that is the differential equation you will get if you solve from a typical method. And you get this. Again, these are not important. So you can imagine if you project 1 to x, you will get this curve. This is the probability of finding the particle at location x. Not probability, the square is the probability. Right? This is the amplitude of the wave function. And this is for the third level. I'm not going to test this slide, but any questions? Okay, but here is important because we keep talking about simple harmonic oscillator, but how is this resemble to the classical one? In classical one, isn't that I should have a ball try to oscillate from left to right, And then when it has the maximum displacement, it has zero energy because it converts all the kinetic energy to potential energy. When you reach this point, this is all potential energy. And then you go back and convert all potential energy to kinetic energy. Because at this point, you don't have potential energy, you only have kinetic energy. But none of this showing that, right? Because the probability of finding the particle actually follow the square of this wave function. So we cannot see that. So this is not the classical thing we see. But there is something called coherent state that will correspond to our classical outcome. And I want to introduce one is for homework, another is you will see this very often in the literature. So what is a coherent state? Alpha. It is defined by this. Can you explain this in English? It basically says the annihilation operator times the coherent state equals the number times that coherent state. So it means what? The coherent state is an eigenvector of the annihilation operator. Okay? This is the definition, right? And it also says that alpha is an eigenstate of the annihilation operator. But you need to know that this is something called, it is not orthonormal. Right? When we talk about the eigenstates so far, usually they're orthonormal to each other. And also there's something called overcomplete. What does it mean? For example, if I have a two-dimensional state, I have x hat, y hat, these two bases is complete. It can represent any state on the two-dimensional space, right? Full linear combination. If I add one more vector, I say this is a part of the basis states, then it's overcomplete, right? Because you don't need three vectors. So same for here. If I want to construct the whole space, I actually don't need all this alpha, right? So this is overcomplete. Just know that it has this. If one day you need to go deeper, you know what to do, right? But coherent states is equivalent to this. Now, and what is alpha? It turned out to be this. You don't need to memorize. Maybe I should, equal to this. Let me write it down. What do you see? Maybe someone describe to me. How do you form the coherent state based on this equation? First, it is what? It's a linear combination of what? Very good. It is the linear combination of all the number states, right? Or the eigenstate of the energy eigenstate. And it's scaled by some factor. One is square root n factorial, fine. This is a constant. But another is alpha to the power n. So alpha is exactly this number that characterizes the coherent state. Yeah, so it's just a linear combination. I think this light is a Poisson. I forgot it's a Poisson distribution light scaling. You do this linear combination, you will get a simple harmonic oscillator, a classical behavior. So basically, our classical oscillation is this linear combination. Okay, so you can see that here show the probability of finding the particle at position x as a function of time from Wikipedia. Right? You see that it travels very fast when you go to 0 and very slow when you go to the edge of the oscillator. This is exactly what we feel in classical sense. Okay, so in the homework you need to prove that this is indeed the coherent, indeed the eigenstate of A. Okay. Okay, I spent a lot of time. Any questions? Yeah. You mean this one? Yeah, this one I did not study. I actually don't know what you mean by cutting at different location. So yeah, you need to look at the code. So I cannot comment on this. But yes, good observation. Yeah. Okay, so these are the summary. You can go back to take a look, right? Although I only have 5 minutes, but I